office, I realized that I absorbed something from TED, which was that my office is a complete mess, which those of you will recall what Ted's office looked like. So, and on a more serious note, I think, looking back, I think we all absorb things from TED without even, realizing it. And, Ted was such an independent scientist. He did things the way he thought they should be done. And really without worrying about what other people would think of his work. It was really what he thought was the right way to do it. And, I think of my own career, which has been kind of independent, and I often do things differently than most people do them. And for better or worse, I think that's due to TED. I thought I would do some science today, even though I can, all these memories are coming back. So I'm going to talk about our work on the core of the Earth, which I began when I was here with TED. But of course, it's moved in directions I could never imagine. So, you can read that. I have some colleagues. So Nadia, I'll tell you when to. Okay. So yeah, go ahead. Yeah. Oh, okay. I might need that. So TED did do work on the core, especially in the early and mid-1980s with Jean-Louis Lemuel, a dear friend and colleague of his in France. And most of it, of course, was using data for inversions of trying to understand core motions. So I just put that up so that you can see that. OK, next one. So I'll give a quick outline of the talk. I'm first going to talk a little bit about inner core anisotropy. So this has been an observation that's been around for about 30 years. In fact, last year we had a nice meeting in Grenoble celebrating this discovery. And the basic observation, which I can show you right now, is that seismic waves going through the inner core of the Earth are anisotropic. That is, they travel faster in one direction than in another. And in particular, they're faster parallel to the spin axis and slower in this direction. Now, this is with body waves. It's also been observed with normal modes. And presumably, this is telling us something about the structure and the evolution of the Earth's inner core. It's kind of an astounding discovery, given the fact that there's so much material on top. And in fact, what people usually do is, because the lower mantle is so complex, seismologists often look at differential travel times. That is, they look at the BC phase minus the DF phase, and they look at the travel time difference. And because the outer core is fairly homogeneous, given that it's a liquid, the differences are due to the structure in the top of the inner core. So I'll just show quickly some data. If you go to the next. Yeah. Oh, yeah, that's right. Yeah, I was looking at the other one. So, this is, a seismogram. I think this is from a paper by Jiadan Song about 20 years ago. And you can see that what they've done here is they've aligned the BC arrivals. Those are the ones that go through the outer core. And then the DF arrivals, I don't know if you can see this, but this comes in earlier than this. And this is from a earthquake and station that's primarily north-south, as opposed to this one, which is more equatorial. So the idea is that this, going through the inner core, is more slow than this. So that's the sort of basic observation. Now, since then, it's gotten more complex. But for us, that's fine. Actually, go back one slide. Thanks, Nadia. Actually, yeah, one more, actually. So that's the basic observation. Now, I'm not a seismologist, although I actually started off at MIT thinking I wanted to be a seismologist. And then, I got interested in the core. And at the time, Ted was the only person here, might still be, or I'm not sure if anybody here is now, working on the core. And even though I was more interested in dynamics as opposed to data, Ted, being the kind of scientist that he was, he accepted me as a student, and we really learned together. In fact, if now we go forward, I remember, yeah, keep going, one more. Yeah, this one here. So this is from a very well-known paper in rotating fluids by Fritz Busse. And what it shows is that in a rotating fluid, that the convection occurs in these very narrow columns in sort of a necklace circumscribing the inner core. And that has to do with the constraints of rotation. It's a style of convection which is pretty surprising, really, although obviously we know that rotating fluids have all kinds of interesting behavior. So it's a very mathematical paper. And I remember Ted and I, we must have spent days and days and days trying to digest what was going on. And this figure sort of makes it more clear, but the paper was, is just such a difficult paper. And I remember we felt so good when we really figured out what was going on. And it's funny because this paper has actually then become important in my own subsequent work. So, sort of like the mantle, which maybe some of you are more familiar with, anisotropy is often due to deformation. When you move solid material, you often tend to align crystals and things like that. And that's, I think, often thought to be the cause of anisotropy in the mantle. But in the core, it's not clear what's causing the deformation. But one hypothesis, which was due to a group working out of Japan, Kuro Sumida, and this was in the late 1990s, is that if convection is more efficient in the equatorial regions because of those columns bringing fluid outwards, then the convection allows the inner core to grow not spherical, but slightly pancake-shaped. And then, of course, that's out of the gravitational equipotential, so it tends to squeeze back to the sphere, although, of course, due to rotation, there's also, it's slightly oblate anyway. And so this plastic flow might cause the seismic anisotropy. Well, it's not clear. The stresses involved are very, very small, so it's not clear that this is happening, but it's certainly interesting. Now, at the same time, we had been studying solidification for completely unrelated reasons. We had gotten interested in problems in solidification. Now, the Earth's core is an alloy, iron and something else. We don't know what else it is, although there's a lot of ideas. And it turns out that when alloys solidify, they solidify in a very unusual fashion that you're not really used to, which is that they solidify in the form of these things called dendrites. So I won't go into the sort of cause for this. It's an instability of the liquid-solid surface. This is a photograph. These are ammonium chloride crystals that are growing out of an aqueous solution. And they have this interesting morphology. If you go to the next slide, thanks, Nadia. So we had been doing work on metallic alloys. So this is a zinc-tin alloy. And the reason that we're using zinc is that it's hexagonal close packed, which is thought to be the crystal structure of iron under high pressure. So the dark here is the zinc-rich phase, and the light is the tin-rich phase. And so these are also dendrites. They don't have all the little side branches and that quite as beautiful structure that the ammonium chloride crystals do, but it's a similar sort of thing. Now, I guess go to the next slide, please. Thanks. So this is the structure of these crystals that have this dendritic structure. So you get these crystals with these little dendrites. And the important thing is that these dendrites, that is those little, those elongated structures that you saw, they grow in particular crystallographic directions. They also grow in the direction of heat flow. So what that means is that the direction of heat flow becomes a preferred crystallographic direction, and that one gets anisotropy. So we showed this, if you go to the next slide. So this is, these are some pole figures showing the orientation of certain crystal directions. And you can see that there's a structure to it. Again, I'm not going to go into that. So if you go to the next slide, please. That led us to a paper which we published in Nature in the late 1990s, which shows these are these crystals. Obviously, this is a cartoon, but these are these elongated crystals with the little dendrite arms. This is a longitudinal cross-section, so this is the North Pole and the South Pole. And as in that cartoon, and also the mathematical figure or the figure from that very mathematical paper that I showed you, if the heat flow is primarily in this direction, that would then tend to mean that this is a preferred crystallographic direction. So it was sort of an exciting paper, and a lot of people liked it, a lot of people didn't like it. And one of the primary criticisms is that even though this might be occurring, and there is some evidence from meteorites that are thought to be planetoid cores and things like that, that this kind of solidification is occurring. One of the arguments is that after the solidification, there's deformation, and that deformation is going to tend to obliterate whatever was present during solidification. So, following our nose, I didn't know anything about deformation. In fact, one of my many regrets is some of you may recall, do you remember that big sand experiment, the tank that he had? Right? Once a year, Ted would make a measurement on this. It was about this long and this wide, and I can't remember exactly how he was applying the stresses, but he would make a measurement of and being stupid, I used to ask a little bit, but not enough, So here it is. I need to learn about deformation, So I should have learned it from Ted, but I didn't, So if you go to the next slide, thanks. So we have begun, this is now ongoing, we have begun to learn about deformation. So what we do is we take our directionally solidified zinc tin samples, that's this here, so that has that kind of microstructure that I showed you in the previous slide. And the question then is, what happens if you then begin to deform it? So this goes into a furnace that we built, and you can see these little gripping teeth, and so we give it a very small strain rate, which we monitor, and we measure the torque as we do this. And of course, we make more than one measurement a year, but they do take, these experiments take weeks and weeks and weeks. I guess if I was as patient as Ted, I could, I could go once a year, but So and we do this at high temperature. I should tell you, we bring it back up to just below the melting temperature. The core of the Earth, or the inner core, is obviously below the melting temperature of pure iron. So we do this at a high homologous temperature. All right. So this is a sort of picture of the things that we get. So you can actually see those columnar crystals. And this is just a photograph. These are millimeter markings here. Under a microscope, you can also see the residue of those dendrites as well. But what you're looking at here are the crystals. This is a foil marker that you can show the deformation. This one actually was not deformed that much. Some of them we deformed quite a bit more. After we do this, we then perform metallography on the samples, and we look at it under an electron microscope to do crystal orientation work. So I'm not going to show you too many details, but I will show you one slide here, which is this is kind of a messy graph, which I haven't really yet fixed up. But this is time in minutes, so 20,000 is already a couple of weeks. I apologize. The torque is in inch-pounds. I haven't converted it yet to it's because the strain gauge is calibrated, and it's an American instrument, and I guess it's mostly used in engineering, and it's a little embarrassing, but it's midterm time, so I just haven't done it. Anyway, so we have here all these curves, and the thing that's really interesting is that the torque begins to increase as a function of time. Now, most materials, most solids, eventually they reach a regime where the torque would level off, the stress would level off. That's the plastic flow regime. But this is indicating that there's what's called hardening going on. And we don't fully understand this. We have a hypothesis, which is that these columnar crystals, iron again and zinc here is hexagonal close packed, and there are relatively few slip planes in hexagonal materials. That is, it's fairly difficult to move these materials. And you need 5 independent slip systems to accommodate any arbitrary deformation. That doesn't exist in these columnar crystals that have this structure. And so as a result, our hypothesis is that it begins to get harder and harder to deform this material. Now, we need to do more work to confirm this. But the result could be interesting, very interesting, because iron, again, in the Earth's core, in the inner core, is thought to be relatively soft, because that's the usual assumption, because it's at high temperature. But this indicates that, in fact, even though these alloys could be at high temperature, they could be much harder than one would expect, just given a naive high temperature prediction. So anyway, this is ongoing work, but I thought, what the heck, I'll show it. And I think that's pretty much it. I was trying to keep within the 20 minutes. I think I might have done my job, right? Keep Earl happy and everybody. So, this is pretty much just summarizing, I think, what I talked about. The last thing is, again, very current work, so that's unclear. But the rest of this I talked about. So I think that's it. I have a lot of memories, but I guess later we can share some of them. I'll just, in case I don't get a chance, I will say one, which actually is more memory of Randy, who overlapped almost entirely with me. So I don't know if I was one of those people that Ted drafted more because of hockey, because I did play hockey. And we had a pretty good team. We were in the B League, And that was amazing. Everybody was 25, and there was Ted, 65, and he was better than anybody else out there. But I do remember, I don't know if you remember this, Randy, that people used to come over. Carolyn sometimes would come, and she played too. But I remember one time, one of the other players, some 25-year-old on the other team, checked Ted. And I remember I could hear him. He jumps up and he yells, "Hey, don't do that. That's my advisor." I don't know if you remember that. But that was the funniest thing. It was the funniest thing. So anyway, but that's all. I don't know if there's any questions or. Yeah.
So if this hardening is going on in the inner core, how does that going to affect, or how does that tie in with like the seismic?
So the question is, if that hardening is occurring, how does that affect, some of the seismic results? And the answer is that it makes deformation that much more difficult. So in some sense, it constrains the types of anisotropy one can get from the deformation. So so the answer, I guess, to your question is that it makes a deformation texture potentially more difficult to get. You can't just get any texture that one might find seismically. So in some ways it makes it yet that much more puzzling, because we really still have a hard time explaining this anisotropy. The other thing also is that it affects the viscosity of the inner core. The viscosity of the inner core is sort of a big deal in terms of all sorts of things like locking of the inner core to the mantle, which you may have heard of. That was in the news a lot 20 years ago, and things like that. So the viscosity of the inner core, which is affected by this, is a big deal for lots of dynamical processes in the core. So, all right.
What happened to that deformation bit, by the way? The thing with the elastic?
Yeah, I don't know. Does anybody know, actually? I mean, I'm telling you, I wish I had paid more attention to that. Does anybody know?
This is the sandbox.
The sandbox. Yeah, do you know?
Yeah, this is a great tragedy.
Oh, no.
The sandbox got thrown away. And so we've had to build a new one. So there is now a new sandbox that Brian Evans built on the 7th floor out in the hallway. You want to go and
oh yeah, I'll have to go take a look at that, actually. So were they able to? I mean, were they able to continue the same deformation process though? I mean, or they pretty much had to start over?
Well, we run this experiment all the time with clean sand.
Right, except Ted's experiment had been going on for, I don't know how long, right? So, right. But it's on the 7th floor, yeah.
If we go back far enough, whatever happened to the water tank?
Ooh, I don't remember the water tank, actually.
In Building 20.
That was before my time. Nice. All righty.
For all the comments.
Yeah.
Thank you.